Everybody, just want to welcome you to Module 3, Lecture 2 for ME 144 Heat Transfer. This is going to cover material and example problems from Chapter 2 in the textbook. So for this Module 3.2, we're continuing on with our introduction to conduction, but now what we're going to do is we're going to apply the concepts and equations that we saw in the lecture for Module 3.1 to some example problems. So within this module, we're going to go over some applications where we can utilize the theory and key equations from Module 3.1, apply these key equations to some problem solving, and I'm going to go through my hand solution to a couple different of these problems from Chapter 2. So let's take a look at example problem 2.57 from our textbook here. In this problem here, they tell us that we have a plain wall with constant properties and no internal heat generation. And this is shown down below in this figure right here. And this is initially at a uniform temperature given to us as T sub I, so I being our initial temperature right there. And suddenly this surface is going to be exposed and heated by a fluid at T infinity at this distance x equals L. So we come out here to this distance x equals L over here. And what we see here now is this T sub infinity of the surrounding fluid here that's going to heat the wall at that distance. And this is going to have a heat transfer coefficient given to us by the value h right here. Now they also tell us that our boundary at x equals 0 is going to be perfectly insulated. So right here, here's our insulation right here. So this is perfectly insulated. And that's going to help simplify down the solution to our problem here. So in part A, which is what we're going to solve for in this problem here with my hand solution, what do they want us to do? Well, they want us to write a differential equation and identify the boundary and initial conditions that could be used to determine the temperature as a function of position and also as a function of time in the wall. So temperature as a function of position and temperature as a function of time. So this is part A of the problem. Now if we kept going with this here for a more advanced problem, we could look at B, C, and D for what they want us to find. So for part B, if we were going to go forward with this here, on the TX coordinates, sketch the temperature distributions for the following conditions. So they're going to give us our initial conditions here, that time is less than or equal to 0, and the steady state condition where time is infinity. So we'd want to actually sketch these out for those two cases there, for initial conditions and the steady state condition, and the two intermediate times. Now in part C, we're using different coordinates here. This is heat flux in the x direction and time. They want us to sketch the heat flux at the locations where x is equal to 0 and then x is equal to L. That is to show qualitatively how the heat flux right here, when we have an x is equal to 0 at some time and the x is equal to L with some time here, are going to vary with different times. And last, we have part D. In part D, they want us to write an expression for the total energy transferred to the wall per unit volume of the wall in units of joules per meter squared. So if we were going to continue on with a longer, more advanced problem, we'd go through, do all our other sketches, and then calculate our total energy as well. But for this problem here, we're just going to figure out how to set this up and do the very beginning part here in part A as we go through my hand solution. So the first thing we really want to do with these problems right here is, one, create a setup page, and on that setup page, simplify down our initial diagram to something more like this here, like a schematic, and I'll show up my hand solution to the schematic here. So you can see as we relate this back to our given diagram here, there's our insulation right there, there's our insulation right there. Then we have our X being measured from this point on the wall right there, going over to this point, over to some distance L over here, and we can see now we have our temperature distribution. We can see our temperature X when time is equal to 0 is our initial temperature. So wherever it is there when our time is 0, this is our T sub I right there given to us in our problem statement there. And we have the temperature of our surrounding fluid and our H value there. And what we can see is that the temperature of our fluid is going to be greater than our initial temperature. So this is all stuff we're going to include on our setup page, in this case here for our diagram. So now that we've had the opportunity to read through that problem statement and look at our initial given diagram, the next thing that we want to do here is create our setup page. So on our setup page, we have the name of the problem that we're doing right here, what all of our given information is that we can get from the problem statement and the initial diagram, a simplified version of the diagram over here with our variable names that relate back to our variables over here in our givens. Then also we'll create what we're looking for and any assumptions we're making as well on the following slide. When we're talking about our givens, we read through this problem statement again, and we see we have our T sub I. So I have my variable name here, and if it had given us any units or numerical values, we'd include it here. In this case here, it left it in general terms. So our T sub I is our uniform temperature of the plane wall. Our X here is equal to L. So we can see here if we go a distance in our x direction from the plane wall, we get up to our other wall over here, L. We can see I have our T sub infinity, which is our fluid temperature, and our H, which is our convection heat transfer coefficient, where our boundary at x equals 0 is going to be perfectly insulated right here. So at x equals 0, this right here is perfectly insulated. So there's our insulation right there again. Now we can see there's our fluid temperature, surrounding fluid temperature there, our T sub infinity, and our H, our convection heat transfer coefficient right there. Our temperature, our initial temperature here, when time is equal to 0, it's equal to T sub I. And we have the relationship here that the fluid temperature right here of our surrounding gas over here, or surrounding fluid over here, is T sub infinity is going to be greater than our initial temperature. So the next thing we want to do is continue reading through that problem statement and now figure out what they're asking us to solve for. Now, if we're to solve this entire problem out, there'd be 4 different things that we're solving for, but we're just going to stick with part A here. So in part A, they want us to find the differential equation to identify boundary and initial conditions. So that's all we're going to do for this problem here. If we were going to continue on for part B, C, and D, what we would then do is for B, we'd sketch out, so we're asking for a sketch in both B and C. For part B, we're sketching the temperature distribution, Tx coordinates, for our T less than or equal to 0, and for T approaching infinity, and the 2 intermediate times. So then, for part C, we'd be sketching the heat flux right here on our Q, or heat flux and time coordinate system here, at the locations of x equals 0 and x equals L. So right at the insulation wall, and then right at the other wall over there, we're at L. And we're going to show how these vary with time. And then for part D, if we're going to do that, we look for an expression for total energy transferred to the wall per unit volume with these given units here. So what are our assumptions that we can make from what we've seen in the problem statement, initial given diagrams? One, it's a 1D construction is what we're going to be dealing with here. We're dealing with constant properties and no internal heat generations. This is going to simplify down our solution substantially. Now, for our first step in the solution here, what we want to do is come up with our general governing equation right here. So in order to come up with that general governing equation, we can look back at the problem statement, flip back to our setup page, and on our setup page, we can take a look. Okay, here's everything that they've given me. Here's what they're asking me to solve for. What equation can I use that's going to relate those things? So we look at this as heat equations, what we're looking for 1D conduction with constant properties. So what general equations do we know that we can use for that there? Well, we have this relationship here from our textbook here for a general equation, where we have here d dx of k dt dx right here, which our K is our thermal conductivity, is equal to our density times our specific heat times right here now our change in temperature with respect to time, our partial change in temperature with respect to time right there. Well, this whole term on the right here is our energy storage term right there. Now, one thing that we can note, we can simplify this down a little bit here. We have this relationship for thermal diffusivity over here in units of meters per second squared, where alpha is equal to our K, our thermal conductivity, divided by our mass density right here times our specific heat. So we can rearrange this equation here and simplify it down. And when we plug in this relationship for our alpha term, what we end up with is we have the second partial derivative of temperature with respect to our distance in the x direction is equal to 1 over this alpha term, our thermal diffusivity term, times our partial of temperature with respect to time. So now we have distance and time in here with our general heat equation here. So this again comes from our general equation here, the relationship between alpha, and then we can plug that in to come up with a simplified version down here. So this is something that we always want to think about and do, is always I like to start with the most general equation that we can reference in the book, because we're not necessarily always going to have the very specific equations memorized for every potential situation. But if we know what general equation to start with and reference and modify that fits the needs of our specific problem, that is a very, very good skill to have. So now what I want to do is go back to my setup page, go back to my initial problem statement, and remember and recall what it is exactly they asked us to solve for. So in part A, which is what I'm going to do for my hand solution, they've asked us to solve for 2 separate things here. The first thing they asked us to solve for was this differential equation here, our heat equation here, and that's what we've done so far. We've come up with this relationship here that I've clearly boxed in and labeled as this is my solution to part A right here, and this is my second partial of temperature with respect to distance is equal to my 1 over my alpha terms times my by delta T over delta T here, or the change in temperature with respect to time over right here. So this is the first part of part A, but I'm not done with part A. The next thing that I need to do is identify the boundary and the initial conditions that can be used to determine the temperature as a function of position and time on the wall. So we need to come up with these boundary and initial conditions that we're going to use in the second part of part A. So now that we've had the opportunity to read through the problem statement, understand exactly what it is they're giving us for information, what they're asking us to solve for, taking that information and coming up with our governing equation for the problem, our next step in our solution now is to look at our initial conditions and our boundary conditions here that are given in the problem statement here. So for our boundary conditions here, we see we have a uniform temperature right here, and we know initially our T sub I right here when our time is equal to 0. So our temperature when time is equal to 0 is equal to T sub I, our initial temperature there. We also see for the adiabatic surface over here, when we're right at that surface right there, when x is equal to 0 at that point there, we have this relationship here that dt dx, the change in temperature, our partial change in temperature with respect to that position when x is equal to 0 is equal to 0 right there. So our temperature is not going to change when we're at x is equal to 0. Then we also have surface convection. Now where does convection occur? We go back to our diagram, we can see that fluid is over off the other opposite side of the wall where x is a distance L away from our initial starting point, our initial surface temperature right there. At this distance L, this is where we're going to have surface convection. And this is given by this following relationship here, where we have negative K times our delta Tx, or our partial temperature with respect to position, which, where does this come from? This is our heat flux relationship. And this comes up here, if we look right here, this comes back from equation 2.6 in our textbook for this relationship here. So we plug that down in here for our heat flux in the x direction. And this is equal to H times, now we have our temperature distribution right here of T of L comma T. So this is where X right here is equal to L at some time, minus our temperature difference right here of our surrounding fluid temperature here. So that is for our surface convection, which occurs where X is equal to L. So now we go back up to part A in our problem statement and back to our setup page. Reference back, okay, we answered the first part of part A, we found the differential equation. Now we've come up and identified our boundary conditions and initial conditions that can be used to determine the temperature as a function of position and time in the wall. And we've clearly labeled these here for these different conditions here, right here. So our value, our conditions right here when x is equal to L, x is equal to 0, and t is less than 0 right here, we have these following conditions that we've now identified. So that completes our solution to part A of the problem. So now it's just a quick overview here. We went through, we read through our problem statement, we created this setup page, we developed our governing equations, we went through and solved out by hand all of part A, the two different things it asked us to solve for. Now how do we do this here? Well, we came up with general assumptions. Our assumptions were three different things here. The first thing we assumed was one-dimensional conduction. The second thing we assumed were constant properties. And the third thing was that there is no internal heat generation. Now for our analysis, what we did for part A, right here, is we went for the one-dimensional conduction with constant properties for this right here, we came up with our heat equation. And the heat equation we found to be this relationship right here. And that was the beginning part of part A. The second part of part A was asking us to find our boundary conditions and initial conditions right here. So the conditions we labeled here, and I've typed these out a little bit neater than my handwriting here. We can see these are relationships right here. So this is the top one is for a uniform temperature, adiabatic surface, and then our surface convection down here when x is equal to L. So we need to physically, again, think about these things. How does it relate to our problem? Okay, at x equals L, there's only this surface convection going on that I'm concerned with for our problem with the assumptions we made. When x is equal to 0, well, I'm right at that adiabatic surface right there. So those are things we need to physically think about, and that's why having that initial setup page is so important for us, so we can quickly reference back to it and visualize, okay, there's my diagram, there's my given conditions right here, here's what I'm solving for, here's how it physically relates. Now, even though for this problem here, I'm only going through up to part A, I have included the solutions here for parts B, C, and D. So please feel free to reference through these and take a look. If we did want to be, this is where we're asking us to sketch this, they want us to sketch the temperature distributions so we can see the results down here. And again, take a look at this, relate it back to your initial different diagram. How do we come up with our axes for sketching out this temperature distribution? Well, they're here. Here's our surface right here. We know at that surface, there's our initial temperature right there. There is our distance L over here, where convection occurs over in our x direction right here. Here is our T sub I, our initial right here. here when our time is equal to 0, and here is our t sub infinity over there. And then if we were to go ahead and plot this and actually solve this out, this is what your final solution would look like. So I would encourage you to go through, practice these, and you can see what the final result is. These will be great practice as you're moving through and doing some of your homework problems or going through some of the other example problems in the book. So I did the same thing here and plotted out. Here's our sketch here for the heat flux right here again. So this is, again, just for you to reference. If you choose to go through and do C and D by hand as well, you can see right there. And our total energy transferred will end up having the relationship shown here right there. So these are the units you wanted in the end right here. This is how we've reduced this down. So again, I'm not going to go through B, C, and D with my hand solutions, but I have included the final answers for you guys to go back and reference if you want to go through and practice this problem. So let's take a look at problem number 2.37 from our textbook here. In this problem here, what they tell us is that we have a steady state temperature distribution, and this is in a semi-transparent material, and they tell us that the thermal conductivity is K right here, and they also let us know that our thickness is L, and that this is going to be exposed to laser irradiation, and they give us the form of that laser irradiation by this relationship shown here, where T of X, our temperature as a relationship to X, is equal to negative A over K, where K is our thermal conductivity, and lowercase a squared, where uppercase and lowercase a are both known constants. And this is 2 the times e to the negative ax power, where again right here a is still a constant, a known constant right here. And this is plus bx plus c, where b and c are also known constants. Now for this situation here, radiation absorption of the material is manifested by a distributed heat generation term right here, our Q dot of X. Now we have this given diagram down here where we can see there's our semi-transparent medium that we discussed right there. So that's all this in our light gray right there. Then we can see our laser irradiation coming down on top surface over there. This is our top surface where X is equal to 0. We're going to move down here in the X direction until we get to this distance L down here, where L again is this thickness of that layer right there of our semi-transparent medium. Now they ask us to solve for 3 different things within this problem statement here, A, B, and C. We'll deal with each of these separately. In part A, what do they want us to do? In part A, they want us to obtain expressions for the conductive heat fluxes at the front and the rear surfaces. So at both those surfaces, we're going to need to come up with these expressions for the conductive heat fluxes. Now in part B, they want us to come up with an expression for this Q dot of X, or our distributed heat generation term right there. In part C, what we need to do is derive an expression for the rate at which radiation is absorbed by the entire material per unit surface area. Now, we're given a lot of things as constants right here, so what they want us to do is express our results in terms of these known constants as if they were actual values that they had given us for this problem statement. Also, not only the A, lowercase a, B, and C, but also our thermal conductivity K and this thickness L we're going to use there. So again, our answer will be in terms of all of those constant values. Now that we've had the opportunity to read through the initial problem statement and take a look at the given diagram, the next thing we want to do is create our setup page here. So again, on our setup page, we have all the information pertaining to what problem it is. And if this were a homework assignment, you'd have your name, the due date, and everything listed up here as well. Then what we want to do is figure out what they've given us and what they're asking us to solve for. So in this problem, what they've given us here is we have our thermal conductivity. And again, these are all given as constant values. They don't give us a numerical value in units. They tell us, okay, K is our thermal conductivity, and that's a known constant value there. L is a known value there, which is the thickness exposed to laser irradiation. And then they also give us this temperature distribution right here by this relationship down here of T of X that we've discussed there, where our A, lowercase a, B, and C are going to all be known constants within that there. And radiation absorption in the material is manifested by a distributed heat generation term that they tell us right here, which is one of the things we're going to solve for relative to the other known constants up there of Q dot of X. So this is the first part of our setup page. Next, we're going to talk about what they want us to solve for. So what they want us to find in here is 3 different things. We'll label them A, B, and C, solving them and keeping them all separately. But again, right on this first setup page so we can quickly reference back to them there. So we have here in part A, what are they asking us to find? Well, they want us to find the expressions for the conduction heat fluxes at the front and rear surfaces, so both the front and rear surfaces. They want us to find in part B an expression for our Q dot of X, and in part C an expression for the absorbed radiation per unit surface area. So again, this is just summarizing everything we read from the problem statement initial diagram, putting it all in one easy to locate location on our setup page here. Now within this here, there are some assumptions that we can make to simplify down our solution. We list those assumptions out here on our setup page as well. So we're going to make 4 basic assumptions right here. 1, we're assuming a steady state. 2, we're assuming 1D conduction in the medium. 3, we're assuming constant properties. And the 4th assumption we'll make is that all laser irradiation is absorbed and can be characterized by an internal volumetric heat generation term, which is this Q dot of X here that we're going to solve for. So now that we've had the opportunity to read through that problem statement, look at the initial given diagram, and come up with our setup page, from that information on our setup page, when we know what we have and what we're looking for, we can start our solution there. So with our solution here, the first thing that I do is kind of draw out a simplified version of our diagram so we can see what's going on right here. So we have up here when X is 0 and when X is L down here. So we have the top surface and the bottom surface down here. Here's our E sub G inside of our semi-transparent medium right there. And then we have given to us our general equations. This is nice. We have the first governing equation given to us in the problem statement for our temperature distribution. So from there, with all this information, what we want to do is what other governing equations, what are the key equations that we're going to use to solve for what they've asked us to solve in A, B, and C. Well, the first thing that comes to mind when we're looking at all that given information, what they're asking us to solve for, is to go back to Fourier's law. And this is equation 2.3 on page 70 of our textbook there. So we go here, okay, our heat flux Q of the X, heat flux in the X direction, is equal to our negative K, our thermal conductivity, times our partial temperature with respect to X, delta T, delta X right here, where this is our temperature right there. So what do we do with this? What is the importance of this being our temperature? Well, then we can plug this relationship that's given in our problem statement down here into this relationship here. So that's exactly what we do as we move along with our solution. We go to Fourier's law as our general governing equation for this here. And again, this is equation 2.3 on page 70 of our textbook here. So we start off with this equation right here for our heat flux in the X direction. And we see that this temperature right here is what we're going to get from what was given to us in our problem statement for our T of X for our temperature distribution. So we're going to plug this value in to our governing equation 2.3 right here. And when we do that, we end up with this relationship here. Our heat flux in the X direction is equal to our negative K times ddx of this whole thing here, which is when we plug in for our T of X there. So this is our negative A, and we've rearranged this just slightly over our Ka squared times e to the negative ax plus bx plus c right here. So now what we want to do is we'll distribute this through and take the partial with respect to x of each of these terms right here. We can see there is an x in the first term here, there is an x in the second term here, but there is no x. This is just a constant value right here. So when we take the partial with respect to x, we take the partial with respect to this first term, then we take the partial with respect to x of b of x, and then we take the partial with respect to x of just a constant. So the partial with respect to x of a constant right there simply becomes 0. So that last term, our c term, is going to drop away when we're plugging into our Fourier's law for heat flux. So with any of these problems, we really want to take the time to separate things out, solve for each individual thing separately. It's a very overwhelming long equation to just try to go through it all at once. So what I'm going to do now is take an intermediate step here. I'm going to say, okay, for this first term here, what I want to do is I want to pull out my constants. Well, what are constants? Well, they told us in the problem statement, our A, our K, and our A are all constants right there. So this whole term right here can get pulled out front of our d dx right here, our partial with respect to x. We pull that out front as a constant right there. Then we're just taking the partial with respect to x of e to the ax. Well, that's something that we know, and we do have a general form for that there. And we'll come down here now and we'll see d over dx, our partial with respect to x of e to the negative ax. If we look up the general form for that there, that is negative a. So we take our a from our exponent up here, bring it down in front, negative a times e to the ax right there is our partial with respect to x of e to the negative ax there. Then we have over here, I haven't touched this yet, this is just simply over here, d over dx of our bx right there. If we were to take the partial of that, we'll find that now becomes just a b right there. The partial with respect to x of bx is just b right there. And again, that c term is 0. So then we go down and we plug this value in now here for our d over dx of e to the negative ax is just negative a, e to the x there. And we have our constants out front still here. So we see our negative a right there times divided by our k, a squared there. And again, this was just what was inside our brackets here. Outside of the bracket here, going back to Fourier's law, we still have this negative k value there, and this is equal to our heat flux in our x direction. So from there, we can see there are a couple things that we could, if we wanted to, reduce and simplify as we're moving through here. But let's not quite do that yet. Let's just leave it in general form right now. And we're talking about two different surfaces. So the first surface they want us to solve for here was our front surface. So what is our front surface? Our front surface is when our x is equal to 0. So for our front surface, what we're going to do is go into this general equation now that we've developed for heat flux from Fourier's law and our given relationship for T of x right here, and plug in that x is equal to 0 for this front surface there. So go in everywhere there's an x. Well, there's only an x in one spot right here, where this is putting this right here as a 0 for our x there. So e to the 0 is equal to 1. So this right here is going to just be 1 right there, just leaving us with a negative a down here. So again, this whole term now goes to just 1. So we're just left with negative a to the 1, or just a negative a. I just did one thing at a time. Step by step, piecewise, take our time, do out each individual step so we don't get lost, we don't drop any negatives, we don't lose anything along the way. We do that there. Now we say, okay, now our heat flux, x direction is equal to negative k times, now we still have this value out here from our constants here of a negative a over k, a lowercase a squared. And we look here, I have a negative there and I have a negative there. We can cancel out these negatives there, eliminate that. That makes life easy dealing with sign convention now there. So then again, piece by piece, baby steps here. Our heat flux is equal to our negative k right here, times now we look at this here of a over ka squared right there times our a plus b. Well, now let's distribute our k through here, right this here. So we can take this k, distribute it through, and we can say, okay, this k here now comes into the top of this equation there, and it comes over here in front of the b there. But when we do that and we distribute that k, we see a lot of things cancel out now. We can see this k on the numerator cancels the k on the denominator. This a over here cancels the squared from this a here. So this reduces down even further now, and we see now, okay, our heat flux here in our x direction is equal to our negative. And we can see now here a over a, capital A over little lowercase a here, plus our thermal conductivity times our constant b right there. So this is for our front surface, the case where x is equal to 0. We now have this relationship down here. So the other thing they asked us to do was the rear surface. Well, what is the rear surface as opposed to our front surface here? If our front surface when x is equal to 0, our rear surface is when x is equal to L. So that's what we have here. Now we're going to go through the x is equal to L. This is why I kept this in general form here to begin with. What I do is right here for this x, I'm going to plug in that fact that this is x equals L for our rear surface. So when I do that, I plug in x equals L. And again, I'm taking multiple steps, baby steps along the way. I'm stating out in my solution everything that I'm doing. That way I can look back through my work and understand what's going on. The grader could look at your work, your teammate could look at your work, your coworker can follow through and clearly understand what you've done each step along the way. So we do that there. We plug in our x is equal to L right there. There's our right there. X is equal to L. So our heat flux is equal to our negative k, negative thermal conductivity, times this whole relationship of these constants here, which is a negative sign out front there, times now when we plugged in here, we have our negative a e to the negative al there. Well, plus our b. Now what we can see is here, well, this negative sign cancels with this negative sign. Those cancel out. Again, helps us with sign convention. So now we have our heat flux here in the x direction is equal to our negative k, negative thermal conductivity, times this whole thing in brackets here. Now the negatives are gone, so we just have this ratio here of our constants, our capital A, our thermal conductivity, and our a squared there. Then we have a to the e, a times e to the negative al up there, plus our b. Well, we can do the same thing we did in our first portion of this problem here. Distribute this k through. We do that. Take this k, multiply by there, multiply it by our b. We end up with our k right here of positive ka over our ka squared there. The k's cancel there. Multiplying it through, applying it through over here. We see we have an a there. It's canceled with a square right there. So we're just left with e to the negative al there. And then we have our kb term over here when we distribute that k through. So we reduce those down, cancel it out, and we see now for our rear surface, when x is equal to L, we have this relationship here that our heat flux in the x direction is equal to negative, this whole term right here, of a over a, which are constants right there, times e to the negative al, plus our kb term there. And again, this is for x equals L for our rear surface that they'd asked us to solve for. So now we can go through, look back at our setup page and determine, yes, I've solved for everything they'd asked me to solve for in part A, and that's the beauty of having that setup page. We don't have to go back and reread the problem statement and look through that. We can just flip back to that first setup page. Okay, I've accomplished everything for both those surfaces for part A. Now I can move on to part B. So for part B, the first thing that we want to do is come up with our general governing equation. As we solve through for this here, we take a look at what they've given us, what they're asking us to solve for, and we realize that a good general governing equation comes from equation 2.19 on page 85 of our textbook, which is our heat diffusion equation there. So we write that out there in general terms to begin with. I always like to start with these in general terms, and then we can reduce it, simplify it, expand it for our specific given problem that we're solving for. So we say, okay, our partial with respect to x right here of k with our partial of t with respect to x there, plus our q dot is equal to 0, and our general heat diffusion equation there. What we want to do is we want to solve for this q dot right there, so we can rearrange this and solve for q dot. And when we do that there, okay, I'm just going to subtract my q dot over here, move it over to this side, so that's the first baby step right there, move my q dot over there, so negative q dot is equal to k times the partial with respect to x of our partial of t with respect to x right there. Well, I want to move our negative sign away and just solve for q dot positive, so I say q dot is equal to, move the negative to the other side as we move things around, negative thermal conductivity times d over dx of our delta t over delta x right there. So then, again, just like we did in part A, we have a relationship for this T here, our temperature distribution with respect to X right there. So our Tx is given to us by this long evolved equation that we can now plug in there. So now you can see why this was good that we rearranged this rather than plugging that directly into our 2.19 governing equation. It would have been even more long and involved than we had to right there. So we can plug that back in right there for that there. But now let's recall. We've already, in the previous part of this problem, we've already solved for this relationship right here, our partial of this temperature distribution right here for our Tx right there. So we've already solved for that in part A. So this whole term we can now plug in for with what we solved for in part A, which is this relationship that we see right here. So this whole term can go right in now for this partial of T with respect to X when we plug in this T of X right there. So now what we can do is we can take that information, put this back in to our heat generation equation here that we're asked to solve for in the problem statement in part B right here. So we go back up into that general equation right there. So our Q dot right here, our distributed heat generation term, is equal to, when we plug in right there, our negative K, our negative thermal conductivity, times the partial with respect to X of this entire term here that we just plugged in now. So this is, again, all of these are constants right here. Our A, our thermal conductivity, our lowercase a are all constants there, times now our negative A e to the negative AX plus our constant value B. So what we can do now is we figure out what are constants. How can we simplify this down and reduce it to make this a little bit easier for us to solve? Well, the first thing we can do is pull out our constants. So this whole thing here is a constant, and this A term here is a constant. So we can do two things in the one step here. One, we'll distribute this through right here, and we'll pull out the constants. So we distribute this through here, pull out the constants first. So these, all of this right here are constant values out front of our partial with respect to X. Distribute through again to our B over here. This is D over dx of B. So now, leave our constants out front right here and say, okay, what is our partial with respect to X of e to the negative AX? Well, this right here is a general form right here, which we solved for previously in part A, and this is negative A e to the negative AX, so we can pull that down when we take the partial with respect to X of our e to the negative AX, becomes this here, and we think of partial with respect to X of a constant, well, that's simply going to go to 0, so this becomes 0 right there, so this reduces everything down, simplifies it a little bit. So this is now all times our negative K, our thermal conductivity out front right here. So let's take a look and see what we have going on. Well, we can see, okay, there's a negative sign there and a negative sign there. Let's cancel those out so we don't have to worry about sign convention mistakes. And we can see an A squared there and an A squared there. Those can cancel out. So this can reduce down a little further. So then we're left with, when we reduce those canceled out, we have our negative thermal conductivity times our constants here of our capital A over our thermal conductivity K there, times e to the negative AX there. Well, we have a K here and a K here. Those can cancel out, still leaving us our negative out front there. Reduce that down, and now we're left with our capital A constant right here, times e to the negative AX. So this is now our relationship here for our distributed heat generation term right here. Our Q dot right there is equal to negative, this whole term right here, A times e to the negative AX. So now that completes everything they asked us to solve for in part B. And this is something that's important that we ask ourselves along the way with these multi-step problems right here is, did we solve for everything they asked for in the entire problem and in each part of the problem? So we can reference back to that setup page that we created, and that's why it's great that we have that. We can go back, take a look, part B. Yes, I have completed everything they've asked me to solve for in part B, but there still is a part C that I need to solve for now. So this is part C here, and in part C, what did they ask us to solve for? They asked us to find an expression for the absorbed radiation per unit surface area here. So this is where we want to find our E dot G right here. So in order to solve for this here, we need to figure out what is our governing equation for now for part C. So each individual part of the way, we're still going to find the general form of our governing equation that we want to utilize. In this case right here, we're going to perform an energy balance. We have this as our general equation right here, where we have our E dot in, or our rate of energy transferred into the control volume, minus our E dot out, which is the rate of energy transferred out of the control volume, plus our E dot sub G right here, where this, we recognize that this represents the absorbed radiation, which is our given right here is our E dot sub G, and that's what we're looking to solve for. So this right here says that this is all equal to 0 down here. Well, we want to solve for this right here, solve for our E dot sub G right there, and if we rearrange this, what we say that this is now equal to our negative E dot in plus our negative E dot out, or our negative rate of energy transfer into the control volume plus our rate of energy out of the control volume. Now, one thing that we note here is when we plug in for our general terms for these two right here, this is going to be our negative heat flux at 0. So this is at a surface right here. What is our 0 surface? This is our front surface right here, our heat flux 0 here, and this is for our Q dot X at L. So our input and our output, and we can go back over here to our diagram that we see over on the right here. Here is our input right here from the front surface. Here is our output over here at the rear surface. So our heat flux coming in, our heat flux coming out, and here's our E sub G right here, which we're going to solve for right there. So the thing to think about, though, is have we already solved for this? So we can reference back to parts A and parts B of our problem here, and we realize that we've already solved for these in part A of our problem there. So we can plug right in for our heat flux at the front surface and our heat flux at the rear surface into this problem here now for our energy balance equation here. So we plug that right in here, and we can say our heat flux right here at our front surface, where X is equal to 0, is this relationship here. We have negative capital A over lowercase a, which are both constant values, plus our K value, which is the constant, times our B value, which is the constant there. So that all goes into this term here. And then for at our rear surface here, where our X is equal to L right there, we can plug in, notice this is a minus here of negative A over A, which are constant there, times E to the negative AL, plus our KB term right there. And we plug those in. We do that, and we end up with this relationship shown here, where E dot sub G is equal to a negative, so those are going to cancel out right there. When we plug this as a negative term that plugs into this here, so there's a negative and negative come to positive. Again, sign convention is very important. That's why breaking things down in terms of individual steps really helps us with that there. Times A over A plus our K right here times B. Minus over here, now we're dealing with our term over here related to our rear surface when X is equal to L. When we plugged in there, we have our A over A times E to the negative AL plus KB right there. We cancel those negatives out. We end up with this relationship down here. So again, those negatives are now gone. It becomes a positive there. Then we take a look at this and say, okay, what can we do to further reduce this down and simplify it? Well, these are all individual terms. We'll move our brackets now here, and we can see we have a positive KB and a negative KB because this negative distributes through when we remove the brackets right there. So this KB cancels with this KB here, and what we're left with, so E dot G over here is going to be, which again, this is our absorbed radiation right here, is equal to A over A minus A over A times E to the negative AL. So bringing that equation we just had from the previous slide over here, one thing that we can notice here is that we have a capital A over lowercase a right here in both these sides here. So we could pull that out front right now, and we do that right there. We can now see that we can come up with this expression for our absorbed radiation per unit surface area, our E dot sub G, as, when we pull this out here, capital A over lowercase a times 1 minus E to the negative AL. Now, there is another way that we can solve this, and that's one thing that's important. There is never necessarily one direct way that we have to use every single time to solve it. There's multiple ways that we can do this. Some ways you may prefer to others, some might be easier, more straightforward. Some you can avoid calculus, some you need to use calculus. So right here, if we decide to use calculus right here, we can solve by integration over the volume. So again, we remember this is they're asking us to solve for the expression of absorbed radiation per unit surface area right here, right now. So we can do this right here using integration right here. And we can use this general term right here, where we have our E dot sub G is equal to the integral from 0 to L. So again, from the two different surfaces right there, one being X equals 0, one being X is equal to L. So those are our X values right there that we're plugging in and integrating over. And this is of our q dot of x right here, dx, where we already have an expression for this. We've already solved for an expression for this right here. So we have this relationship from part B, so we can plug this right here back in now for this q dot of x right there. So we plug that in, that's a times e to the negative ax, and now we can go through our calculus steps. When we complete this, we should end up with the same answer that we see here. So it could be two different ways to solve it, one better preferred than the other, or you could solve it both ways as a double check to make sure you did your work right. So we do that there. We start off with this general term right here that I've boxed up above. And again, this is we're plugging in from part B here for our q dot of x right there. We plug that in to this general equation here. And now we end up with this relationship here. And we can start doing our calculus, do our integration here. Well, with any integration right here, the thing we want to do is pull out any constants out front of our integral right there. Well, we know this a value here is a constant, so we can pull this out front right here. And then we're left with just the integral from 0 to L of e to the negative ax dx. We can go to a table of integrals, go back to our calculus book, look up from a reference table here, and recall that the integral of e to the ax is equal to 1 over a times e to the ax there. So we can do that and plug it in now down here when we do out this problem. And we do that there, replace the integral of e to the ax with this negative 1 over negative a times e to the negative ax right there, because we did have that negative up top here, which was different than this here. So we have this negative down here when we pull this down to the negative out front there. So it's a 1 over negative a times e to the ax, evaluated again now from x is equal to 0 to x is equal to L right there. So plug those in as our terms of integration right there. Well, we can also, let's say, reduce this down first before we plug those in and say, okay, well, I can see that this negative a, we can pull this out front here. Now I have my e dot sub g is equal to a over a times e to the negative ax from 0 to L. So already seeing we're starting to get close to that form that we saw before. So now we pull over the top here the expression that we have from the previous slide right here. So again, we pulled out this negative a out front here. So now we have our e dot sub g is equal to our capital A over lowercase a negative times e to the negative ax evaluated from where x is equal to 0 at one surface and x is equal to L at the other surface there. So we can plug these in and solve them separately. So we plug in our 0 over here for our x. We end up with this left-hand side of the term. We plug in our L for our x. We end up with this right-hand side of the term over here. So we can say on our left-hand side, when we plug in our x is equal to L, we have our constants a over negative a out front here times e to the negative al, minus on our right side of the equation here where we plug in x is equal to 0, we have the same a over negative a out front, but now we have e to the negative a times 0. Well, a times 0 is 0, and e to the 0 becomes a 1, which drops this whole term down there to just a minus a over negative a, and we can see that that negative there cancels with that negative there. What we can do now is we can pull that out front of an a over a. We can pull that term out front right there, and we do that right there. We now have an expression here of a over a times this 1, because this right here relates to this term right here, minus for this term over here of e to the negative al right here, which does double check with our solution that we had before. We go back, what did they ask us to solve for in C? Say they wanted us to derive an expression for the rate at which radiation is absorbed in the entire material per unit surface. That's exactly what we solved for here. We've now completed parts A, B, and C for this problem.